To send an electrical signal, we need two wires. Since two metal conductors are by definition a capacitor, this means that each section of our transmission line has some capacitance. And since a loop of wire is by definition an inductor, each section of our line also has some inductance. Suppose we close a switch, applying a constant DC voltage across our two wires. This capacitance and inductance is what prevents the signal from traveling instantaneously. Therefore, we can never eliminate this capacitance and inductance completely, because this would then violate Einstein's theory of relativity, which states that information can never travel faster than the speed of light. These capacitors and inductors shown are not components that we deliberately add to a circuit, but are an inherent part of all wires that carry electrical signals. When electric circuits appear to behave in unpredictable ways that seem to violate the laws of physics, this is often due to the capacitance and the inductance of the wires. In this instance, for example, the signal keeps bouncing back and forth between the beginning and the end of this transmission line. With nothing connected to the end of the line, the voltage at the end of the transmission line reaches double the value of the DC input voltage from the battery, and the signal is then reflected back. Reflections can also occur at the connection between two transmission lines which have different amounts of capacitance and inductance, in which case only a portion of the signal's energy is transmitted to the next line, and the rest of the energy is reflected back. Suppose we connect a short circuit at the end of a transmission line. What will happen when this signal reaches this short circuit? As always, the speed with which a signal travels depends on the capacitance and inductance of each section of the wire. When the signal reaches the short circuit, the signal is reflected, but with the voltage flipped upside down. If the impedance at the end of the line is too low, it will behave like a short circuit. And if the impedance is too high, it will behave like an open circuit, both of which cause reflections. But if we place just the right amount of impedance at the end of the line for the amount of capacitance and inductance in each section of the line, then the amount of reflection can be minimized. Reducing reflections is desirable, as reflections can significantly interfere with the proper operation of a circuit.